Well, hello everyone. My name is Emily and this is Grace, and we're going to introduce you guys to a project called LitterNET, where we detect litter within Harnessville Park. So a little bit about our background for this project is that in Harnessville Park, we noticed that there was a lot of litter near eating areas, especially within the playground, and that these eating areas were relatively far from trash bins, and that's why we decided to focus on this issue, because litter can kind of make an area feel unwelcoming. So we did some research on what current litter detection systems do, and we found that there is not much literature on real-time litter detection. Most of it is focused on static images. So you have a car that moves around, takes pictures, but the driver knows that there's no litter in this area, or there is litter in this area, and analyzes that. And current literature also focuses on neural network models such as YOLO, EfficientNet, R-CNN. And these would have to cost a lot of resources to train them and make sure they're accurate. And there's also a plastical data set. This is an open source data set on litter in multiple backgrounds, like at a beach, things like that. And then our inspiration for LitterNET, particularly our background subtraction part, comes from literature on vandalism detection. We found an article on real-time vandalism detection where they focused on static changes within a predefined area, such as where a stop sign is, right? And we wanted to focus on that sort of logic.
So our project goals for this was to optimize real-time detection through a preliminary background subtraction step, and to perform homography mapping using OpenCV's homography functions so that we could map litter onto a top-down map of Harnessville Park.
And I'd like to put some emphasis on this image that kind of shows a proof of concept of what we wanted to do. Since our goal is kind of to give the model more focused regions of interest, you can see here that when we have a far off image, even though the data set is trained on images like this, it produces higher accuracy when you have a close-up. So here are some methods. Our algorithm is given an input video of a person littering in real time. So there's a frame where they're not in the scene, there's a frame when they enter, and there's a frame when they leave. And we use background subtraction to kind of detect when that person comes in or leaves. So, and with this background subtraction, we kind of find contours that say, oh, this is a person moving across the scene, and then we conduct our analysis once they leave. So we have a background update where we compare the initial background model from the background subtraction to what the scene looks like after they leave. And this is good for kind of detecting any static changes that happened in the background, like if someone left a backpack or if they left a plastic water bottle. And then we send these smaller focused ROIs to a model, and such as YOLO or RFD.
How does that, can you explain a little bit how the ROI identification works? So you difference them.
Yes.
You end up with the differenced image, and then you can tell where the areas are where there have been changes. How does your bounding box algorithm work? Do you progressively scale it? Do you find the center and progressively scale till it's...
Basically, yeah. So once it compares the scene to the previous background model, it produces a binary image based off of contours that have changed, the static changes, such as this water bottle, and then it basically puts a bounding box around that white area, and that is the image that is saved.
I see. So you calculate. So I'm just imagining in your implementation, if you have, let's say that you have two areas where there is significant difference. So you see two white blobs, for example.
Yes.
Do you generate one bounding box, or is it two?
No, it's two. The contours are separate from each other.
How does it work?
We could do a demonstration, I guess, to show.
Just at the highest level, how are you, I guess first question is, how do you determine how many white blobs there are?
Oh, we use OpenCV. We use OpenCV absolute differencing, and also OpenCV's function find contours. And
I see.
Find static changes from there.
When you do find contours, does it return a set of contours?
Yes.
Okay, and so the cardinality of that set is the number of bounding boxes you have to generate? I see, and then so for each one of those contours, are you calculating, is OpenCV generating the bounding box, or are you calculating min and max on the X and the Y's?
We use like OpenCV bounding rectangle, and then we increase this to have like a padding around it.
Got it.
So that there's some space, like some here on this image, you can see how it is the water bottle, but there is some padding alongside it, so it's not directly on the bottle.
Got it, cool, thanks.
So after we detect the litter, our goal is to map it. And we do this with OpenCV's homography features. So OpenCV's homography works by finding landmarks and creating a homography matrix using the pixel coordinates of where they are. So the homography matrix is a 3x3 NumPy array, and this basically tells when you input a coordinate, which will be in the form of x, y, 1, it will go through the homography matrix and it'll be able to calculate what it would look like after being transformed onto the map image of the park. So because we want this to be applicable and usable, we decided to make a GUI built with Tkinter. And this is supposed to support the easy access to a system of cameras within the park. It has functions that allows you to add new cameras and open up cameras. And whenever you add a camera, you obviously need to adjust the homography so that it can transform points from that camera. So we've also made an adjustable homography mapping system where the user can select the landmarks for the homography from the interface. And this basically allows for the easy addition of new cameras around different spots of the park.
So here are our results. We basically tested several models and sort of differentiate between their confidence with the LitterNET background subtraction step or without. And we found that there was a significant increase in true positives when we applied this LitterNET algorithm. As you can see for RFETR, there's like about a 10 to 15% increase, while for our YOLO models, the change is more significant.
So in conclusion, we believe that the advantages of our program is that it increases confidence in true litter, in actual litter, and it produces less false positives. So for our future work, we hope to do more model training to make this more accurate and also implement the differentiation of different types of trash because we believe there's a lot to be learned from what kind of trash is in the park. Specifically, when we went to the park, we saw quite a lot of alcohol there, so we think that could also have like some kind of importance to what's going on in the community. We also want to include more brightness normalization and occlusion features. Right now, we do have those with the background subtraction, but we hope to make it more accurate in the future. And we also hope to implement this into a physical system with more cameras because that is essentially what our program is being built for. We also hope to have improved resistance to shadows because when there's like lighting changes like shadows, that often causes like errors. So we hope to make that more accurate in the future.
Oh, for the background differencing, right? You get bigger, sort of big white blobs of the difference. Okay, gotcha. Would you mind going back one slide? I had a question now, I don't know if I remember it. So just to be sure I understand, so here you're looking at just taking YOLO V11 as an example. You were testing running YOLO V11 on the full image, no differencing.
Yes, we're running it on a video, frame by frame, seeing how well it detects the trash that somebody drops.
Okay, and then with the differencing, do you run YOLO V11 only within the bounding boxes?
Yes.
Okay, very nice. And the results are very good.
And these are our references, and thank you. Any questions?
Did you?
Why don't you show us the interface and also the demonstration.
Okay, so when I run this, it's gonna run the background subtraction here. So this is the quick, no, this is a video.
Oh,
Pre-saved.
you shouldn't have told him. Should have been like, gotta do more.
Oh yeah, just keep waving.
Oh yeah, it's all the way.
Okay, so here's Grace. She comes here and drops a water bottle. So our problem with the OpenCV background subtraction, our initial idea was to like use that background subtraction to kind of detect when the water bottle is dropped too. But as you can see, the water bottle quickly disappears once the object walks by if it's not moving. So that's why we had a different step where we add the weighted frames and use absolute differencing instead. And we have the background subtraction just for the object movement. And then here it saves some ROIs. So here it saves like this car, for instance, that came into the thing. Some shadows, this is where we wanted some improved resistance to shadows. The adding the weighted frames, this was good for detecting shadows that would quickly come by and go, such as like if a tree moves around really quickly, but if a shadow stays in a certain place for a long time, that does count as a difference.
I think I missed the weighted frames. How does it work?
So after every frame as it's running, it basically combines the two images using OpenCV, and that's what we're using for the comparison. So I've actually saved, this is like the averaged image, so you can see the water.
Oh, I see, yeah.
Is there a little bit of the shadow different, and then this is the initial background image where water was not there.
Oh, I see. You're averaging across the frames to get rid of the stuff that's moving about.
Yes.
Gotcha.
So like, for instance, that's why you don't see Grace walking by, because she's only in a frame
Yeah.
for like 1 or 2
But
frames.
the persistent
as she
stuff
moves
sticks
across.
around.
Yes.
Super cool.
And then this is the threshold image, and this is where some of the false ROIs come from that are eliminated once you use the model. So here, this is the water bottle that we wanted to focus on, and the other ones, this is from the car, right here, and it saves this. So if I run a different video, for instance, where there's not any trees, let me delete these. So this next video that I'm gonna play is within the library. I come by, I drop trash in the frame, I leave, I come back, and I drop some more, and I leave the frame. It detects both of these pieces of trash. So once I run this, here we are. Okay, there's me. I walk by, I drop some trash. The video is a little too big for my computer to display properly, but you can see I'm still holding the other piece of trash in my hand once I just left. And then I come back.
Can you hit that maximize button? Let's see if that scales.
Still mission. I drop it, and I walk away. And then here's the initial background. Right? There's no trash here. And then here's the average weighted. You see the 2 trash in the presence, but I'm not there.
And sorry, it's average. At what point do you begin the average weighting?
The average weighting is done per frame, and the absolute difference is done once the object leaves.
But in order to get, so imagine that you have 100 frames, and the litter appears in frame 100. If you're averaging, if you're doing weighted averaging across the frames, it doesn't really show up at frame 100.
True. If someone is still in the frame by the time the video ends, then it's not going to detect that trash. That's why this is more made for a surveillance type of thing, where there is going to be people coming and going and leaving. There's
Oh,
always
sorry, I
gonna be-
misunderstood. So the whole thing is triggered on entry and exit of people.
Yes.
Ah, clever. Yeah, got it.
And then here's a difference image where the trash is highlighted in white, and since we don't have any shadows that stay in place for long, you don't see any of those other weird dots. Yeah.
Yeah,
Not sure
this
what the
is-
difference.
This is the interface. It looks kind of bland right now, but we just have all our feature functions on the top. So this requires you to upload your like map, and then that is your camera view over there. So that's would be the camera's perspective. And using this, you should be able to select video point. Oh, just. So using this, you should be able to select video points and image points, and this is for the homography. Shit, that's right there.
Is this just from the webcam? The video quality is super good.
This is from videos from our phones.
Oh, that's why it's so good.
Try one.
Try one.
Try one. Maybe your camera got broken again.
Oh.
Oh, there we go.
Oh.
That's me, guys.
So basically,
That's, I didn't know.
so this is supposed to save your cameras into arrays, and then these arrays like store, they're also arrays that store your maps and your camera views for each camera. So this is how it would work with a working camera. So you would upload like the index each time of the camera. And I'm not sure why the homography is not working today. Let me try the.
Oh, I think if you're doing real-time code edits, I think it's super high risk.
Yeah. Yeah, so this is before we like moved everything together, but there might be some problems with the moved one. I'll have to debug that later. But as you can see, red dots appear where like I click. So that is basically the purpose of it. We haven't gotten to try this with a real camera yet. We've been using inferencing and videos for now. But, so we've been manually clicking where the litter is, and basically it translates to where that would be on the map. And we hope to like get like a lot of this and like collect where most litter is on the map.
That's super cool. Grace, I saw that same video on the news. They were reporting FAU students throwing trash in the street. No, this is awesome. Any other things that you'd like to show us in the demo or in the code?
This is the selecting video points feature. This is what we made for easy selection of like the homography and like creating the homography matrix. So basically, I'm going to choose 4 points, and the ones I have been using so far are this one, and these are the edges of the sidewalk. And then I've been using like the lower hump, like the falling of the statue in the back. I just click on it, and then there's the light post in the left, and yeah. After you click 4 points, it closes automatically, and then you can also select the image points for it, which would be the corresponding points to the ones you just picked in the right order, so that it can calculate correctly, and then you can press that to calculate it, and then the inferencing should work. Yeah. So that's what we made for easy access.
Super cool.
Code.
Yes, you did a great job.